Okay, very warm welcome everyone to this Cosmos seminar. Today we host Professor José Senovilla. He will talk about singularity theorems in gravitation. Thank you very much for being here today, and I leave it to you.
Thank you. I don't know if you can see my screen now. I made some changes, and is it okay?
Yes, we can see it. Yeah.
Okay. Okay, so thank you for the invitation, and I hope the subject will be of interest to the audience. I am giving you some summary of singularity theorems in gravitation, uh, and oh, something is wrong. I knew. Sorry, I have to do something here.
Don't worry.
I don't know. Where is this here? Yeah, probably now is better. Yeah. So this is the outline of my talk. Basically, some history. I will talk about the most important theorem, Penrose's theorem, and then about many other theorems. And after that, there will be a little discussion about the meaning of the theorems, the small print, things that do say and things that do not say, and also a discussion about whether quantum effects can solve the problem. So, as you may know, in 2020, Penrose singularity theorem won the Nobel Prize in Physics. This is probably the first time in history that the mathematical theorem wins a Nobel Prize in Physics. And of course, it was a deserved award because this was published in 1965, and this is a game changer. I mean, before 1965, general relativity was dominated by Einstein and very, very classical things. And this completely changed the theory and started what is now like the modern general relativity with all the surprises like black holes and cosmology and everything like that. And then historically, there were indications of singularities. I'm going to use Penrose diagrams because, as you can read here, this is in the scientific background of the Physics Nobel Prize. These diagrams are indispensable tools in the study of curved spacetime, so I'm going to use them. So, first indication of singularities probably goes back to the solution found by Friedman in 1922. I hope you can see my mouse. These are the Einstein field equations.
Yes.
So this is the metric, and uh, this I use the omega square sort thing for the metric of the unit round sphere. This whole thing then is a metric of a three-sphere, and we have here a function of time, which is called the scale factor. So Friedman, who was a mathematician, didn't think about the universe being static, so he wondered whether there were solutions of Einstein field equations that were dynamical. And then he found this famous solution where the energy momentum tensor is dust, u is the velocity vector, rho is the energy density, here a is a constant, capital A, and this is a solution if the scale factor satisfies this first order ODE that can be solved, but you don't even need to need to solve it because just by looking at the equation, one can very easily prove that as long as the lambda, that is the cosmological constant, this is smaller than this quantity, where rho is the density, then any solution of this equation must have a zero somewhere in the past if the universe is expanding now. But when the function a is zero, you see the whole space metric disappears. This was called by Friedman like the initial time. Here is the Penrose diagram for this particular model. Given that the space is a three-sphere, one can just draw the sphere as a line here, where this is the South Pole and this is the North Pole. And then the whole solution will start in a big bang, and then there will be an expanding phase, but eventually it will start contracting and it will end in a big crunch. So this region here has A dot negative, so this is contracting. Sometimes, Penrose diagrams sometimes are confusing. One has to think about every point here as a round two sphere. Sometimes the best thing to think about these things is to put another copy identically here, and then identify here with the South Pole there. And then you will get like a cylinder, and every circle in the cylinder will mean an instant of time, which is a sphere. Well, the next is the famous Schwarzschild solution found in 1915. This is well known to probably all of you. Here, Rg is the gravitational radius, where m is the mass of the function. Now, there was some initial confusion about the possible singularity at r equals Rg, because this becomes 0. But there is also another singularity at r equals 0, of course. And the first one, the first person to actually identify correctly what is the problem at r equals Rg was Lemaitre, because there was previous discussions by Panlevé, Goldstern, Eddington, and others, but they all believe that they have found different solutions to Einstein equations. So the first one to understand that those solutions were actually Schwarzschild solution in another coordinate system was Lemaitre. And he found this particular coordinate system where you can easily see that r equals Rg, which is also in these coordinates given by that, is a null hypersurface. So the Penrose diagram for Schwarzschild solution in Lemaitre coordinates looks like this. So this is Scri plus and Scri minus, so infinity for null radial geodesics at the past and the future, and this is I plus. And the red region is the region where we now are going to call the black hole region. Right. So as you could see in the previous, there is also this R equals 0 singularity. This is a place where the curvature blows up. So there were some singularities in the Friedman model, also in the Schwarzschild solution, and then Lemaitre, who found the most general solution for dust with spherical symmetry, recognized that this initial singularity was there, and he tried to avoid the too much symmetry, because people started thinking, well, we are having these singularities because we are using very symmetric solutions. And then, following a suggestion by Einstein, he explored other possibilities. In particular, he explored a metric like this one. This is what we call today Bianchi one. And then he proved that the singularity was there anyway. So he wrote this one says that anisotropy can no more prevent vanishing of space than pressure can. And then probably the most important advance was the study of gravitational collapse by Oppenheimer and Snyder. In 1939, they studied the collapse of a ball of dust with a spherical symmetry that was contracting by its own gravitational attraction. And then they found that the collapse is unstoppable and the star goes beyond the values of the gravitational radius until eventually the radius goes to 0. And they produced the first model of a black hole and the first understanding of what we now call a black hole. And I quote from the paper, the star thus tends to close itself off from any communication with the distant observer. Only the gravitational field persists. And although it takes, from the point of view of the distant observer, an infinite time for the asymptotic isolation to be established, for an observer co-moving with stellar matter, this time is finite. And in fact, it can be quite short. So to understand the Oppenheimer's Snyder construction, we already have all that we need, because the Oppenheimer-Snelly construction is built by gluing a part of the Friedman solution with another part of the Schwarzschild solution when has been extended to the black hole region. So the thing is that you take here a value of chi equals constant, and then you cut this part, that is the contracting part of Friedman solution. And then here you take a particular radial time like geodesic, it will look like that, and then you cut there. Here you take the zone on the right, and here you take the zone on the left, and then you match them. For that, of course, you need to comply with some conditions, and in particular, they give you a relation between the parameters on one side and on the other side. And then you get the Penrose diagram of a black hole with a spherical symmetry. Here is this region here in purple is the star that is collapsing. So this will be the part of the diagram that belongs to Friedman. And then, as proven by Oppenheimer-Snyder, they cross the horizon, so the radius gets smaller than the gravitational radius, and then eventually this becomes the singularity. Outside the star, you have a normal situation that we have here outside the sun or something like that, as long as you are very, very far away. And as long as you do not approach the horizon, you will never see the black hole, because everything you will ever see will be the surface of the star. So for you, even if you go to I plus, it will take an infinite time for you to see the production of the black hole. Another thing is whether you are adventurous and you want to enter into the black hole, which is this region here, because you can also do that by just letting yourself fall in vertically. And then if you enter here, then you are doomed. You will not be able to avoid the singularity. Okay. So these were the initial stages of singularities. Now we go to what happens in 1955. This is when Rai Chaudhuri, who is this guy here, found his equation. This is how he wrote the famous Rai Chaudhuri equation. And then we understood about the focusing of geodesics. And this is a picture by Penrose on how geodesics can focus to another point. Okay, so Einstein died in 1955, April 18, and less than a month later, Rai-Chaudhuri's paper was published. This is the Rai-Chaudhuri equation. I mean, if you understand a little bit about geometry, this is the Ricci tensor, and these are covariant derivatives, and the V is just any vector field. But if you choose V to be tangent to geodesics, so the geodesics are those that maximize time, that emanate from either a point or orthogonal to a hypersurface, then this quantity vanishes, because this is the condition of being geodesic. So this quantity here disappears. And also, due to the orthogonality to hypersurfaces, this part is symmetric. So you can rearrange this part, and then you get to the conclusion that the derivative along the vector field itself of the expansion, because this is the divergence of the vector field, is a quantity that happens to be, this term is negative, and this term, depending on the Ricci tensor, may be negative or not. But if you assume that this condition is satisfied, then you prove very easily that this quantity, the expansion of this pencil of geodesics, goes to minus infinity in finite affine parameter, or infinite time, if you prefer. Now, for Rai-Chaudhuri, he thought that physical particles were moving around these geodesics, and then you get a curvature singularity, so things blow up, density and everything. But in general, this is not a singularity. What you predict is a caustic. It's like what we now call either a conjugate point or a focal point. So it's a place where these curves tend to cross each other. And the thing is that this focusing effect is important. I mean, these are called either caustics or focal or conjugate points. But as noted by Hawking and Penrose, these geodesics that are always maximal between two points along the geodesic, if they found one of these conjugate points or caustics, then they stop being maximizing. So this is the important thing that they are going to use for the singularity theorems. So this is called the focusing effect. Now, of course, one needs this condition. This is a condition on the Ricci tensor, and therefore this is a condition on the curvature of the space-time. Anyway, this is called convergence condition in general, but if you are in general relativity, you can use Einstein field equations, and then you can relate this condition with a condition on the energy momentum tensor. And this is why the curvature condition is sometimes called the strong energy condition, if this is satisfied. Now, I want to stress that despite the name of strong energy condition, this is a condition on the curvature, okay? And I want to notice that the lambda term doesn't make any difference if you are dealing with null geodesics. And then we arrive to Penrose's theorem, the one which won the Nobel Prize, 1965. This is the iconic drawing by Penrose himself in his paper. The paper is just 2 pages with this beautiful picture where he proved the first modern singularity theorem. And here, everything that is drawn is important. This C3 thing is a Cauchy hypersurface. This is a trap surface. This is the singularity. And there are many little cones here. And then there is this cylinder, which is the horizon. I will explain a little bit about this. So the Penrose theorem looks like this. If you are in a space-time which is with a metric of sufficient differentiability, and then if you have the convergence condition for the null curves, null geodesics, so this condition on the Ricci tensor, and if you also have a non-compact Cauchy hypersurface, I will tell you what is that. And also if you have a closed future trap surface, and I will also explain that, then there are null geodesics that are incomplete to the future. So this theorem is amazing, but at the time it has two important novelties. First, the characterization of singularities by incompleteness of geodesics. And most importantly, the concept of a trapped surface. This is really, really important. And even today is an amazing concept that allows to do many things concerning black holes. So there is this assumption about the Cauchy hypersurface. A Cauchy hypersurface is an instant of time where one can set good initial value conditions for the space-time. Einstein field equations happen to be a hyperbolic in a mathematical sense, so they are amenable to a initial value problem. And then you have to give initial conditions, and a good place to do that is a Cauchy hypersurface. And in precise sense, this is an achronal hypersurface, so there is no any 2 points on the hypersurface with time separation, such that any causal curve that is endless, so anything that is moving in time, has to cross it once and only once. So the important thing about having a Cauchy hypersurface is that this is equivalent to spacetimes that are called globally hyperbolic. Global hyperbolicity is a property that if you take the set of 4 possible causal curves between any 2 points in your spacetime, this set is compact. And this is equivalent to having a Cauchy hypersurface. This is a tremendous theorem by Giraud. But then if this thing is compact, between any 2 points, the set of all causal curves is compact, then there has to be one that maximizes time. And the one that maximizes has to be a geodesic. Okay, so this implies the existence of maximal geodesics between any two causally related points. Now, whether or not spacetimes are globally hyperbolic, this is related to something else that is called a strong cosmic censorship conjecture, also by Penrose, but we don't have time to talk about that here. Now, the very clever idea by Penrose was to think about incompleteness, because singularity theorems are not theorems proving that any quantity is singular. What they prove is incompleteness of geodesics. Okay, so they should be called incompleteness theorems. The problem is that at singularities, so if you have a singularity like in Friedman or in Schwarzschild, things blow up, and in particular, space-time breaks down. So singularities do not happen in any place or at any time. So this is then we cannot actually talk about where they are or how are they. So Penrose used hypothetical light rays. These are curves that do belong to the space-time, so that they come to a sudden end, right? So they just finish without a reason, right? They don't reach infinity or something like that. And in this sense, they point at singularities, at places where something is happening. And what happens is that then the space-time itself becomes incomplete. Okay. So this was a very clever innovation that avoided many, many difficulties to define rigorously singularity in general relativity. And after that, actually it became like the standard characterization of singularities as proven by the singularity theorems. Just a remark that spacetimes can still be geodesically complete, but singular in the sense that there are non-geodesic curves that are also incomplete, okay? But there are no theorems proving incompleteness of non-geodesic curves so far. And the most important advance created by Penrose in his theorem is this concept of a trapped surface. And this has a funny story behind it, which I want to represent here in this picture. This is written in his book, so it's explained by himself. I mean, he eventually got this very, very clever idea, and he thought, wow, this is amazing. And then he was about to cross a street in London, and something happened, maybe a bus coming or something. And then when he crossed at the other side, he had forgotten completely about that idea. But there was this sense inside his mind that he had found something important that he couldn't remember. And then he was for one full day trying to recover this magic idea until eventually he got it back, and then he wrote his 2-page theorem, sent it to physical review letters, and voila, Nobel Prize 50 years later. Now, what is a trapped surface? So for those of you who like geometry, this is just a space-like surface, so it has codimension 2 in a space-time. And the thing is that how the area of this surface behaves. Now, in traditional geometry, if you have any sphere or any surface with 2 dimensions, and you deform it, so you choose now a vector field at every point of the surface, you choose a vector, you displace this surface by the vector a little bit, and then you see how the area changes. So the vector field here is denoted by psi, and then the variation of the area, one can easily prove that is given by this integral on the surface, on the original one. This is the divergence of the tangent part of psi, the part that is tangent to the surface, plus this scalar product with h, and h is the mean curvature vector. The mean curvature vector of the surface is nothing but a trace of the second fundamental form. Hope you know that, but otherwise I can explain this later. Now, if the surface is compact, the integral of the divergence vanishes by the traditional theorems in mathematics. So you just have this product here. So it's just the product of the vector of the formation, scalar product with the mean curvature vector. Now, in traditional Riemannian geometry, that is with a positive definite metric, any vector is either zero or non-zero, right? I mean, the norm is always positive, or if it is zero, the vector itself is zero. So the only distinguished case in Riemannian geometry were what are called the minimal surfaces. So the area doesn't change when you perturb them. However, in Lorentzian geometry, the vector field can be time-like or null. So it can be with a zero norm without the vector being zero, or it can have a norm that is negative. So when the H is time-like, then if you take any deformation along future time-like vector field C, this product is negative. So the variation is negative. And it doesn't matter which deformation you take as long as it goes to the future. So these are precisely the types of the trap surfaces. So those are having the mean curvature vector future time-like. You can also do the same to the past, and then they are called trap to the past. If the H is not time-like but light-like, then they are called marginally trapped. There is an observation here, but I just want to say, I mean, if you have studied trap surfaces by having the null expansions negative, this is because the expansions along any normal is just the product of the mean curvature vector with the normal. So if this is time-like and this is, for example, null, then this is always negative if they point to the future. Okay, this is mathematics, but what about physics? So why are they called trapped? So let's think about this normal situation. So this is representing a three-dimensional space-time. Okay, time goes to the vertical, upwards, and then we take an instant of time, t equals t naught, and we take here our sphere. So the circle here represents the sphere. Then an infinitesimal time later, dt, if you have sent signals, light signals from the original one towards the exterior and towards the interior, these light rays will form a new surface, a wave surface. And the exterior one is here represented in blue, and the red one is represented in red. And of course, the red one is inside the yellow one, and the blue one outside. And in a normal situation, this will be what happened in the sense that the exterior one will have a bigger area, and the smaller one will have a smaller area. But what happens if the universe is contracting? We know that the universe is expanding, right? So it can also be contracting. This is what happens when a black hole forms. It contracts. So I represent here the contraction by taking my slice of time, a differential time dt later, smaller. So it has shrinked, right? And then I do the same. And then, of course, the blue one is outside the yellow one, and the red one is inside the yellow one. But the important thing here is, what about the yellow one in comparison with the yellow one here, and the blue one in comparison with the yellow one at the original time? And it may happen that the blue has an area that is smaller than the area of the original one at the original time. In other words, it doesn't matter how you go to the future from your surface. It doesn't matter how you go to the future, and of course you have to go to the future. The area a little time later will always be smaller. It doesn't matter whether you run towards the exterior as fast as you can. The area will be smaller, okay? This is why they are called trapped. Okay, so what is the relevance of the singularity theorem for gravitational collapse? Well, again, we can see here the picture, the iconic picture by Penrose, and this is like what you do for Penrose diagrams is, if you can see in the Penrose diagram many little cones. You see a cone here, a cone there, a cone there. These are the light cones, right? So what you do when you want to draw a Penrose diagram is you just force the diagram to have the cones at 45 degrees, okay? So all cones, like here or here or there, now are at 45 degrees with respect to the vertical, okay? And then you just draw the same picture. And the same picture here is basically this one. So the matter is here in red, and there is the Cauchy hypersurface will be something like the horizontal thing here. And this cylinder, which you can see is tangent to the cones everywhere, now becomes at 45 degrees here, and this is the horizon. Now, this is not even, still compactified. Then once you have put the 45 degrees, you just compactify, and then you are able to see infinity here. And then this is the Penrose that the diagram that I showed before. But I want to notice that there is this little s here. This s here is a sphere, right? Because a point in the Penrose diagram is a sphere. And it doesn't matter whether you go towards the exterior or you go towards the interior, given that here now r equals constant are hypersurfaces like this, they always get a smaller value of r, and the area is 4 pi r squared, so the areas decrease. So this S here is a trap surface. And this is what is represented here, like this S2 here, okay? Okay, now the key point about trap surfaces, and this is not usually explained, is that not only they are independent of coordinates, bases, or things like that. I mean, these are things well defined. The decisive thing is that they are stable because their definition relies on inequalities. What do I mean by stable? It means that if you do small perturbations, they will not disappear. Okay, they are stable. Now, the Einstein-Euler field equation, so those describing a fluid, a perfect fluid in general relativity, are hyperbolic in the mathematical sense. And therefore, they possess the property of continuous dependence of the solution on initial conditions. Now, we know that in the Oppenheimer-Snyder collapse, which is a very, very particular model, you form trapped surfaces, trapped spheres in a finite time. And therefore, initial conditions that are close to Oppenheimer-Snyder, but without spherical symmetry and without having a dust, will also lead to the formation of trapped surfaces. And therefore, this is the importance of Penrose's theorem. You prove from what you already know that this collapse to a black hole producing a singularity inside the black hole is a robust thing in classical GR. It doesn't matter whether this is symmetric or not. So what is the relevance for cosmology? Well, Hawking immediately realized that there are trapped spheres, but in its past version in the Friedmann-Lemaitre-Robertson-Walker models. Now, you just take the simplest Friedmann-Lemaitre-Robertson-Walker model. This is just flat in spherical coordinates and the scale factor. Now you take the spheres given by t equals constant, r equals constant, the normal ones. And then if you compute the mean curvature vector, this is what you get. Here, a dot is the derivative of a with respect to t, and then you can compute whether this h is time-like or not in this metric, and it is very easy to see that this is going to be time-like if and only if this happens. However, you can now translate this mathematical condition into something that happens now in our universe. And if you translate this into our universe, this is just telling you that if h naught, so this is the Hubble constant, is larger than c divided by d, where d is the proper distance to the sphere that is centered at us, now the observer, then you see that this is the condition for a past trap surface. So if you take D large enough, so in our universe that is expanding, if you take a very, very large sphere, given by C over its H naught, then it will be past trap, and then you will have a singularity. And again, the important thing here is the stability, because of course our universe will not be Friedman-Lermet-Robertson-Walker, but as long as it is close to Friedman-Lermet-Robertson-Walker, the theorem will follow too, due to the stability of the trap surface. Okay, so let me just now pass to some classical singularity theorems. So once we had this advance with Penrose and then Hawking, there was the simplest singularity theorem was proven by taking this observation that if you assume the convergence condition, there will be focal conjugate points, and then these focal points will invalidate that the geodesics along these causal curves will be maximal. And then you can prove theorems. This is probably the simplest one. You take a space-time. Now you assume that there is a Cauchy hypersurface, and you assume that the trace of the second fundamental form of this Cauchy hypersurface, or if you want, the expansion at the instant of time given by the Cauchy hypersurface, you assume that this is positive, or rather larger than a positive number. And then if the convergence condition hold, then you can prove that all timeline geodesics are incomplete to the past. And the proof is very basic. Once you know the Roy-Choudhury equation, given that sigma is a Cauchy hypersurface, the spacetime is globally hyperbolic, and therefore there is a maximal time-like curve between sigma, the Cauchy hypersurface, and any point. But you know that these maximal curves cannot have any point focal to sigma. However, Roy-Choudhury equation tells you that all of them are going to have focal points, and actually the focal points have to be at the proper time, which is less than that. And therefore, no causal curve can have a length, or if you want, a time greater than t divided by b. So all of them are incomplete to the past. And then many singularity theorems have been proven since 1965. They apply to cosmological situations, to collapse, black holes, gravitation, collision of gravitational waves, and also to inflation and others. But all the theorems have a very precise pattern. And this pattern is like this. What you need is a condition on the curvature. You also need a condition on causality. And then you also need the boundary or initial condition. You need three things, always. And then the conclusion always is either null or time-like incomplete geodesics. So let me tell you a little bit about these conditions. By the way, yeah. So this is the paradigmatic case. This is the so-called Hawking-Penrose theorem, published in 1970 by two of them. And then they have the convergence condition, the causality condition, meaning in this case that there are no closed time-like lines, so you cannot go to your own past. And then they assume also called the generic condition. The generic condition is a condition on the Riemann tensor, which is basically this for any time-like vector u. And then you can assume for the boundary condition any of these three things. You just choose one, either a closed trap surface or a closed achronal set without edge, so this is an instant of time, or a point with reconverging light cone. So a point says that the cone will reconverge, and then you get the incompleteness. So why do you need these assumptions? How do they work? Now, the curvature condition, that usually they are called energy conditions, and also the generic condition, these are the geometric nature, and they are indispensable. You always need something like that, because what you need is to force the geodesic focusing via the Roy-Choudhury equation. So this is the basic thing. Now, physically, this captures the idea the physical property that gravity is attractive, okay? So gravity is always attractive. There are no negative masses. Now the causality condition, on the one hand, it does not allow you to go to your own past. This is okay. But basically, it assures via the existence of a Cauchy hypersurface, for example, sorry, it ensures the existence of maximal geodesics between any two causally related events, right? And then we know from standard mathematics that the maximal geodesics cannot have focal points. So you see there is still some tension because we have focusing of all causal geodesics because of the attractive property of gravity. But if we assume this causality condition, there must exist geodesics that have a maximal proper time joining any two events. And of course, these geodesics cannot have a focal point or a caustic. So there is a kind of already a tension here. However, there is no theorem yet. There is no contradiction, right? And this is important because we don't have a finite upper bound for the proper time of families of time-like geodesics. In other words, we need to get the contradiction another condition, and this is given by the initial or the boundary condition, right? Like the trap surface or the reconvergent light cone or something like that. And then I will, just to explain or to illustrate these ideas, I am going to discuss some singularity field spacetimes for illustration. Because there are many singularity field spacetimes, of course. So for example, basic one, this is called the Einstein static universe. This was the first metric, apart from Schwarzschild, written in GR. This was the famous static solution of Einstein to describe the universe. So this is the three-sphere, a constant here, which is actually a cosmological constant, and then the universe has this density. Now, this metric satisfies the convergence condition. Okay. It's globally hyperbolic, so any t equals constant is a Cauchy hypersurface, and this is compact. Has points with reconverging light cones. This is one of the boundary conditions in the Hawking-Penrose theorem. So it seems that it satisfies all the conditions, but it is geodesically complete. No incompleteness here. What is going on? Well, there is one little assumption in the theorem that is this generic condition. Remember, there was the generic condition. Well, this fails in this particular. So you need all the conditions, and certainly there are solutions that have all these properties, like reconverging light cones, convergence, globally hyperbolicity, but they are still non-singular. Another famous case is the Sitter universe. The Sitter universe, which can be written in these coordinates. Again, this is a three-sphere, but now the square factor is the hyperbolic cosine. Here, little lambda is given by the cosmological constant like that. And this is the traditional Penrose diagram of the sitter. Well, only the red part will be the traditional Penrose diagram of the sitter. But as I mentioned before, any point here will be two sphere, except for those at the North Pole, or the South Pole, and those at the North Pole. So sometimes I like to just put another copy here, which will be, once I have gone from the South to the North Pole, then I go from the North Pole to the South on the other side, and then I just identify this with that, and then I get a cylinder. And every single circle will be one of the three spheres in the sitter. Now, the sitter has trapped spheres, and these 2 points here, I mean, if I only had the red part, this point will be, but if I use this version, then the 2 point will be a two sphere in my circle. And then if I compute the future, that was at 45 degrees, you see this future is, the boundary of the future is compact. The boundary of the future, because here and that, this is identified. And then this compactness is the problem in the Penrose theorem. This is what makes impossible in the Penrose theorem that the spacetime is complete. But this is because he assumes a non-compact Cauchy hypersurface. Here there are Cauchy hypersurfaces. This one, for example, is a Cauchy hypersurface, but it's also compact. And then the compactness of the future of the top surface and the compactness of the Cauchy hypersurface are okay. The contradiction only appears if one of the two is non-compact. So again, this is geodesically complete. This is a solution I found many years ago. You can see that it has kind of cylindrical symmetry, and all the functions are very simple, are cos and hyperbolic sines. This is a solution of Einstein field equations for a perfect fluid without lambda, with this equation of state. This is the very good equation of state for the beginning of the universe. And here the energy density, as you can see, is perfectly regular everywhere because the hyperbolic cosines never vanish. So there is no curvature singularity. You can prove that this solution is geodesically complete and it's also globally hyperbolic. So you take any t equals constant, and this is a global Cauchy hypersurface. Then now you take one of these Cauchy hypersurfaces, you compute the trace of the second fundamental form, or if you prefer the expansion, and this is what you get. And as you can see, this is positive for any positive t. So this seems to comply with the Hawking theorem that requires the convergence condition. Of course, this is satisfied with this equation of state. It requires a Cauchy hypersurface. This is here, the t equals constant at Cauchy hypersurface, and it requires that the k was positive, but not positive. The requirement was that it was larger or equal than a positive constant that is finite. And here this doesn't happen because there is no minimum constant. I mean, this is not bigger than a given positive constant, because if you go to rho very, 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 very large, this k goes to 0. So this little difference makes this singularity free. So this is the typical small print on the singularity theorems. So this is what I have already explained. So in this particular solution, you can see that given global hyperbolicity, you have maximal curves between any 2 points, but still you also have between any 2 points the Focusing effect. And there is no contradiction. And there's no contradiction is because there is no positive limit for k below. It's not bounded below by a positive constant. Okay. Right. And the last one for singularity-free solutions is this. This is what are now called regular black holes. Now there is a boom of regular black holes in the literature. So if you go now to archive, you will see, I don't know, hundreds of papers talking about regular black holes. And in spherical symmetry, they all, or maybe 90% of them, look like that in a Penrose diagram. So this will be like a Schwarzschild area, and then this will be the black hole part, but there is no singularity. The singularity has been removed. Now we have here something that is called a Cauchy horizon, and then we get a regular center. Now, how can these models survive? Because you can always make them to have the convergence condition, etc., etc. Well, the point here is that we have replaced the singularity by the Cauchy horizon. You see, if you take this particular instant of time, this is not a Cauchy hypersurface. Why? Because there are points here that going to the past will never cross it, because they may end here, and remember that this is at infinity. So this is why this is called the Cauchy horizon, because any point beyond that will have curves to the past that will not cross this particular sigma. But there are also more funny things in this diagram, is that you can have this instant of time, or you could have this other instant, or you could have this other instant of time. And they have different topology. This particular one is S2 cross R. So it's two spheres and then R. This particular one is the traditional R3. And this particular one is a three-sphere going from one south pole to the north pole. So there is a change of topology of your space-time, or your space in this case, okay? So you are now having regular things, but all these things are happening. Now I want to make some relevant remarks, and I want to get rid of some myths about the singularity theorems. Sometimes, in particular, the theorem by Penrose was interpreted as proof that black holes form in gravitational collapse. And this is not true, because the things are more subtle. Penrose's theorem assumes the existence of a trapped sphere. And therefore, and I will explain why, it doesn't say anything about the formation of black holes. Why? Well, what it's telling us is something that happens inside black holes, but they have already been formed. Why is that? Well, remember, this is a trap surface in the Penrose diagram, and this is inside the horizon. And there is a famous theorem by Claudel and Hawking that states that in asymptotically flat spacetime, so if your infinity looks like this, any possible trapped sphere that you can place in your spacetime will never stick out of the horizon. You cannot go outside the horizon with any trapped sphere. In other words, trapped spheres are something inside the black hole. And if you assume that you are having a trapped sphere, you are assuming already that there is a black hole, okay? So the theorem doesn't say anything about formation of black holes. It is a result about the interior of black holes. It is telling us something that we will not be able to see ever. Only the theory is telling us if you go inside the black hole, there are trapped surfaces and therefore classical incompleteness. If you want to go to the formation of black holes, then the question is quite another. And there are some results by Christodoulou and other people more recently. How you can form trapped surfaces for initial innocuous data. Another thing I want to mention is the incompleteness. There is no known relation between divergence of the curvature and incompleteness of geodesics. Okay, these are different things. Of course, if the curvature diverges, the geodesics are going to be incomplete there, but not the other way around. And the theorems only prove the incompleteness of geodesics. And then there is a bigger problem, is the problem of extensions. Because as we have seen in this regular black hole, you can take this particular surface, assume that this is a Cauchy hypersurface, and then if this is a Cauchy hypersurface, you are only dealing with this part of the space-time. Of course, you could also take this other one, and then you will be dealing only with this part of the space-time if you want this to be a Cauchy hypersurface, or you could also take that one, where you will only be dealing with this part of the space-time if you want this to be a Cauchy hypersurface. And then the thing is, well, okay, if I want this to be a Cauchy hypersurface, then I know that I'm not having the full space-time. And of course, the theorem applies because you have a non-compact Cauchy hypersurface, you have a trapped sphere here, but the theorem is just telling you that you have geodesics incomplete here. But this is not the real singularity because you can extend the space-time, right? And then the thing is, okay, just extend the space-time. But this is not so simple because physically meaningful extensions are far from obvious. Extensions are not unique, and there are infinite inequivalent choices in general. The analytical ones are not possible in general, and they are not advisable many times. And if you have different extensions, then the new extensions can be extensible themselves, or they can be singular, or maybe they violate I don't know, some energy condition or something like that. So it might seem obvious to choose one of these particular situations, but this is not correct because you may violate a physical condition that you don't want to violate. A typical example is the maximally extended Kerr black hole. So this is the typical Penrose diagram for the Kerr extended spacetime. And so there are two versions because the singularity arises only at the equatorial plane. So the equatorial plane, this is this diagram, and any other different plane will be described by this particular thing when now r equals 0 is a regular place. And then you can go to r going to minus infinity. So this is the traditional maximal extension of the spacetime. But let me tell you something. This is a Cauchy horizon, and then when you come to this region here, they happen to have closed time-like lines. So you can go to your own past just traveling to the future. So violation of causality. So would you like to have this extension or would you prefer some other ones? Okay. So this is a big problem with the theorems. And now I don't know how I'm doing with time, but probably I should just I will skip.
It's very interesting, actually. So I guess that you can mention this part as well. Go ahead, Drew.
Well, I have this yeah, maybe it's only 10 minutes or maybe 5. This is just telling you about the contemporary versions of the theorem because there are some mathematical refinements, so you can get minimum differentiability. So the theorems have been proven even for continuous metrics. You can have uh, you can relate incomplete geodesics to causal edge points of the space-time. You can do this in other things that are non-Lorentzian geometry. So there are many mathematical refinements. You also have theorems talking about inflation and the cosmological constant. These are papers by Good, Borde, Vilenkin mainly. And also when you use scalar fields, you can relax the causality condition, allowing for partial chronology violation. So having even close time-like lines, you can have the singularity theorem. You can relax or generalize the boundary on an initial condition. You can deal with non-trivial topologies. You can remove, just replace the trap surface with something which is only weakly or outer trapped. So these are less trapped. You can have surfaces of any codimension. You can also prove theorems in word products. And then there is the most important thing is the quantum oriented. But this is the last bit of my talk. Let me talk about the quantum gravity as a possible solution. Now, many theoretical physicists believe that the tension between the singularity theorems and a theory of quantum gravity, probably you heard that we don't have any such theory yet, will solve the incompleteness problem. Now, on what grounds? So what is the basis for this? Now, you see, the theorems are telling us that in extreme situations, the space-time, they have an edge, a margin. They cease to exist in a classical way. This is the meaning of incompleteness. However, some violation of the curvature conditions that are implied by quantum effects might help because the main condition that we always assume is the convergence condition. But in a quantum theory, in principle, the energy should not be always positive and things like that. So this is a hope that this will allow us to have something that is not incomplete. But as we are going to see, they do not help in general. So the question is, will the singularity theorems, or at least some kind of them, survive in a full quantum theory of gravity? Okay, so let me just make some comments about that. So the main line of research in this direction consists in relaxing the convergence conditions. Now, there are early results in the last century. So we have results from 1978 by Tipler, by Roman in 1986 and 88, and so on. they were dealing with average energy conditions. So we don't assume that the energy or the curvature condition is satisfied point-like, but only when you integrate along, I don't know, a time-like curve or something like that. There are much improved results given in our century now, 21st century. They reconsider the null convergence condition in quantum field theory. So there are many papers by Fuster and Roman and others. And then, actually, singularity theorems have been proven taking these effects into account. And here you have a list of some of them. Actually, there is a version of the Penrose singularity theorem that allows for global violations of the convergence conditions. Now, what about other quantum inputs? Of course, all that I have said about quantum is just dealing with quantum field theory in curved space-time. But of course, one also has to take into account the quantum fluctuations of the space-time itself. So a truly quantum gravity theory. So you can see a nice discussion in this paper here. Now, classically, one relies on point-wise focusing of causal geodesics, but this cannot simply be true in a quantum regime because there is no point. I mean, there is no way of saying that the particle is at this point with this momentum, right? However, the boundary condition has also been adapted to this quantum situation. For example, the notion of closed trap surface can be adapted to the quantum cases, and you can prove a quantum Penrose singularity theorem. This follows from something that is called the generalized second law of thermodynamics. This generalized second law is nothing but the traditional law plus, so the traditional law that the entropy is always non-negative. But you have to add the entropy of the black holes. So if you add the traditional entropy of the exterior of the universe, exterior to black holes, plus the black hole entropy, then you get the generalized second law. Now, again and again, the Penrose singularity theorem can be proven under these many quantum weaker circumstances. So, for example, a robust singularity theorem in full semi-classical gravity regime was recently announced by Boso, and this excludes controlled bounces in the interior of a black hole and in many, many cosmologies. So this is very, very recent. And also you have singularity theorems in quantum gravity using effective field theory methods. So if you go to second order in the curvature, this has been analyzed, and some theorems disappear, but Penrose's theorem remains unaffected. And then there are gravitational collapse singularity theorems that are consistent with black hole evaporation. So black hole, if you take quantum effects into account, you know that black holes evaporate by Hawking radiation. And there is a very, very recent one that establishes that standard models of evaporating black holes are again non-geodesically incomplete. This is the reference, you see, May 26. In summary, so far, our experience shows that at least some of the incompleteness is a robust result, and the geometrical description of gravity breaks down, even in the quantum realm. So, what is then the meaning of singularity resolution? You see, the typical approaches to remove the spacetime incompleteness, basically using quantum theory or something like that, are based on extensions, like the one of regular black holes, or bounces, replacing the Big Bang singularity, but by a bounce. So there is a contracting phase and then a rebound, and then there is expanding phase. Now, these either extensions or bounces can be motivated by quantum effects or by some quantum gravity would-be theories. Unfortunately, all these resolutions actually remove the singularity, but they create bigger problems. Because in the case, for example, of regular black holes, by accepting the Cauchy horizons, you lose predictability, and also they are generically unstable because the Cauchy horizons are always unstable against small perturbations and they become singularities. So they lead to incompleteness. In the case of the rebounds, of course, you have to choose. either you prefer a birth of time and a birth of the universe or not. And if you like the rebounds, then you have to admit that an infinite time has passed to reach us now. So I don't think these are real, actual resolutions of the singularity problem. In my opinion, the resolution should be an explanation of the classical incompleteness. We have to find something that replaces our continuous space-time and see what happens there. But of course, I don't have the solution. No. So this is my final slice. Just some comments. If you hear the sentence, singularities are commonplace in general relativity, this is wrong, okay? All gravitational systems, you look around yourself, the planets, the moon, the galaxy clusters, whatever you see, they are all ruled by general relativity and they are perfectly regular, okay? So this is not true. General relativity is not a singular theory. The thing is that there are two possible exceptions, the very early universe and the interior of black holes. So this is true. Incompleteness in these two exceptions is a feature of GR, okay? Now, singularity theorems provide supporting evidence that we need something else. I don't know if this will be quantum or not, but we need something else to explain GR in extreme situations, in particular inside black holes. Whether or not the quantum gravity will resolve this problem is something to be seen, and I am skeptical. Okay, and that's all. Thank you. Sorry for the time.
Thank you. Thank you very much. It was a great talk, actually, a great lesson, and a great lecture. And I especially appreciated your considerations regarding the necessity of explaining the incompleteness. We have to explain facts. I mean, science is about that, and physical theories do have this function of explaining. And of course, the GR is not providing to us proper explanations for the singularities and for the behavior of space-time in the cases that you described. And we need something more. And I also appreciate the fact that you leave it open. I mean, it's not at all said that we are on the right track.
Yeah.
To one program or another. Anyway, I first leave it to the people at the talk. If they have questions, please go ahead. Comments. Alessio, Stefano. I can start if you like. I have several
Yeah.
points.
Okay.
Well, first of all, you didn't mention it in your presentation. However, I read your papers and your works, and you you use a concept that is familiar to those working in philosophy, maybe not those working in philosophy of science or philosophy of physics, but for sure to philosophers, to general philosophers, to generalists, which is the following statement. So you say, our understanding of black holes is teleological in nature. Can you please, very briefly, I mean, as you want, but can you comment on this? What do you mean by this teleological? And I agree with that. I mean, and then we discuss on why. Let's see whether we
Okay.
are agreeing on the reason.
Well, this is this is the question is that the typical models of black holes that we use, which are very basic, are usually stationary or static outside. So they are just there forever. And then Yeah, I mean, these are solutions of the equations, etc. But actually, real black holes form and evolve because if you have a real black hole, first it has to be formed somehow, and then maybe it has some kind of accretion disk, and then it's taking mass, etc. And also, you can do things to the black hole because it's there, right? And then what happens is that if you consider this dynamical situation, there is no way to define a black hole unless you know all the future of the space-time. And this is easy to understand, I think, because imagine that you have something which is not a black hole, and you say, okay, I'm not in a black hole. But this is not true because you don't know what is going to happen to the future. And in the future, there may be, I don't know, millions of tons of mass falling into your object and then creating a black hole. And then when you do that, the event horizon appears. But the event horizon is the thing that is teleological. You only know where the event horizon is if you know the entire future, because you can even put some mass, and it will be changing. So you could very, very well be happily living even in flat space-time and already be inside the black hole. And there are very nice Penrose diagrams for that. So actually, once you understand this, that the event horizon is teleological, then the definition of black hole should be changed. And of course, there are better definitions or considerations. But if you want to rely on the event horizon, then you are doomed. I mean, there is no way that this is physically some clear concept, because I insist you need to know the entire history of your universe into the future to know where the event horizon is.
I see. Now this
And
is.
this is the theological thing, yes.
I see your point. Thank you for clarifying this. I also wanted to ask you something that you mentioned in your talk, but I want to make sure that I can connect it to the right literature. So at some point in your presentation, um, you rightly mentioned that an extendable or extensible space-time might not satisfy, for example, energy conditions of GR. So this is a problem that is discussed in a beautiful paper. I find it beautiful from the standpoint of the historian of science in this case. It's a 1972 paper by Gerard Penrose and another colleague. I don't remember the surname now, but Hawking did not sign that paper. It was
Mhm.
1972, and it's about ideal points.
Mhm.
And it's interesting because it comes after the theorem, of course. So and it deals precisely with an implementation, let's put it in this way, of the boundary construction program, but taking into account, of course, the Penrose work and so on. And and they say precisely this. So you can have this beautiful construction. So you insert these aliens, as Vinci called them, these ideal points that allows you to extend, to make space-time extensible. But the point is that they also say, okay, but our way of handling this is not satisfying the energy conditions of GR. It is historically something connected to what you were saying.
Mm. Yes, I mean, I'm not sure about the particular situation that you mentioned, but this is the general problem with extensions.
Yeah.
I mean, it's very easy to understand. If you have something that is extensible, You have to choose where to extend it. And you don't know. There is no rule to do that. There are an infinite number of different extensions. You can take the exterior region of Schwarzschild, and I can produce here, I could give you, I don't know, immediately like 100 extensions, that there are different ones. Because the traditional one you find in the books is you assume that it is vacuum everywhere. Okay. This is one assumption, but I could assume something else, or I can change the symmetry or many things. So the thing is, okay, once you find something that is extensible, how do you extend it? You don't know. And then you say, okay, let's have some reasonable conditions, physical conditions. But then you are in the situation that maybe this extension violates the energy conditions. This other violates the chronology condition, and this other violates something else. And this other. So which one will you choose? And then, so the solution, I mean, not the solution, but what Penrose did was to say, okay, we have all real spacetimes are going to be globally hyperbolic. This means that if you have a Cauchy hypersurface, there is no Cauchy horizon, no extensions. And this is the so-called strong cosmic censorship hypothesis that has not been proven, and occasionally there are counterexamples, but people say that these are, like very limited situations, blah, 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 blah. But this is a big problem. Actually, I don't know if you are aware, I mean, not recently, maybe 3 years ago or something like that, Kerr uh, put a paper on the archive
Yeah.
criticizing Penrose and everything else. Okay. And the problem is that he didn't understand this very basic thing because he was just considering um, his metric,
Mm,
but in the part that is globally hyperbolic. I
mm,
mean, not extended.
mhm,
And then, of course, Penrose's theorem applies because they're incomplete. The only thing is that you can extend them. But in this particular region, they are incomplete. So, yeah, this was the very basic mistake that he made, apart from being uneducated about the things. Yeah, so this is a big problem. The extension problem is a very big problem.
I
I
mean,
guess from the philosophical point of view is also important because it's just that like saying, okay, what do I do with these things? Do I attach new parts of space and time here? How do I do that? Yeah, I don't have the solution. But I always remark in all my papers that this is a very important point. Yes.
absolutely. Okay, so I don't know whether the other people might want to jump in and to ask something to our speaker. Let.
Well, thank you for the very beautiful lessons because it was very interesting. I'm not sure that I catched all the things that you said
Okay.
because it passed a long time since my last lesson on black holes.
Okay.
I have so I have a small question on one thing that you said maybe that I didn't get. At some point, you said that the geometric condition are that you showed are usually connected with the fact that gravity is attractive,
Mhm.
but I can't understand that because I'm sure that GR is already encapsulating the idea that you only have positive mass. Isn't that right? So am I misunderstanding this point? And then I get another curiosity question.
Mm.
You mentioned a lot of semi-classical quantum gravity completion. I was
Mhm.
wondering if there is also some analogous of this kind of the trap surfaces in string theory, if there are any, because I remember that when I used to, I mean, having fun with the five-dimensional black holes,
Mhm.
wrapping deep brains to create such a geometric semi-classical solution. There was no interior of the black holes in that case, but I'm not sure of that. Maybe I can't remember exactly that. So I just want you to tell some more about the other quantum completion. Thank you.
Okay, so about the first question, well, no. I mean the uh, the attractive property of gravity is not immediately encoded in GR. This depends on the property of the Ricci tensor. So this is the property I wrote, that the Ricci tensor contracted with two vectors have to have a sign. The thing is that if you are in GR, you can relate this to the energy momentum tensor because of the Einstein field equations. And then you can talk about positivity of mass or positive density and things like that, right? But it is not encoded. I mean, you can still have energy momentum tensors that violate the energy conditions. Or from the geometrical point of view, you can see things where the Ricci tensor doesn't have this property. And this is actually what people do in.
Now I get it. Like you mean, for example, like for the dark matter and the dark energy and so on.
Yes, for example.
Okay, okay, sorry. Okay, thank you.
Yeah, so it's not incorporated in the theory. And this is what they do in quantum theory, because in quantum theory you can have small regions, a violation of the energy conditions. You can even have negative energy density, things like that. And then you say, okay, now. So for the second question, if you go to string theory, of course, this is even more, in string theory, you have even more possibilities, because in string theory, you live in 10 dimensions. And then there are many more possibilities to have trapped submanifolds. They don't have to be just spheres or codimension two. There will be eight-dimensional things. You can have, 3, 4, 5, 6-dimensional submanifolds that have this property of. And then there are singularity theorems for all these cases. So the trapped things exist there, and there are many more possibilities. But I don't know exactly about the thing that you mentioned. If there is no interior of a black hole, then I don't know, because these trapped things are inside the black hole usually. So,
Thank you.
yeah, my pleasure.
Stefano, do you have something to ask to our speaker, or? Okay, Stefano, maybe he cannot talk. I don't know. He cannot hear me.
Yeah,
I have
okay.
a couple of other points.
Okay.
Exploit your presence, basically, to ask you
Great.
everything. Um, so, um, you see, now I speak as a philosopher. Okay, so um, I will abstract a little bit from my background in physics and so on, from my knowledge, let's say, no, and I will look at what the program that you reconstructed is telling us. Um, so when I look at, for instance, the boundary construction program, this works in the 70s about ideal points and so on and so forth. Um, what um, uh, what seems to me important from the conceptual standpoint is, okay, these are for sure mathematical construction. There is, of course, a study. It is, of course, a study of the extensibility of space-time, and for this reason, we are considering, of course, the structure that is described by the theory. But of course, the energy to meet the energy conditions is fundamental if we do physics, and especially if we do GR. So there is, in a sense, uh, um, an old debate. This was really old. It goes back to the end of the 50s. So 3 years after Einstein's death, Bruno Finzi, who was he was actually working in Italy first at the University of Milan and then at the Polytechnic of Milan. And he, together with some colleagues, had the opportunity to read one of the last papers that Einstein wrote, which was the introduction to an Italian volume for the 50 years of relativity that was published in 1955.
Mm.
I wrote an article about this. It's I mean, it was under review. So it should be out at some point, hopefully in 2026. But Bruno Finzi read Einstein's words, and a few years later, he published a paper that is translated in English as On Gravitational Motion, sul movimento gravitazionale. And in this paper, he talks about the problem of singularity. So, of course, today we talk about singularities, but many years passed, and our meaning of singularity, I suspect, is not the same as the one that not only Einstein but also Finzi had in mind, also because there were even people thinking that, I mean, at the end of the 50s, singularities were something due to the mathematics, to the formalism of the theory. Now, however, Finzi was an expert in fluidodynamics, so he was one of the greatest scholars that we had from the Levi Civita school and so on. And so for him, tensors were like drinking a coffee, you know. So he was he could master relativity theory. He could master
Mhm.
physics, could master Einstein's field equations. And he said, the problem with the singularity in GR is always that you have to insert an alien.
What is it by an alien?
Alien in the theory. Now, if we look at the program of boundary construction, so the program of boundary construction addresses the singularity problem by adding an alien, the boundary.
Mhm.
Program of ideal points address the problem of the singularity by adding ideal points, so by making space-time extensible. But these ideal points are aliens to what? To the theory with respect to GR. Because if we look at the tensors, if we look at the displacement tensors, if we look at the mathematics that is used in GR, these structures are all aliens with respect to the theory. And now I arrive to the point. We always say that Penrose's theorem shows the consistency of the formation from the black hole and the singularity from the gravitational collapse. Um, However, and so we say that in a sense it is included in the theory, this result. But it's also true that at some point he opened something that goes very well beyond GR, I think, because all the study of black holes is showing us that we're trying, by inserting aliens with respect to GR, with respect to the theory, to go beyond it. And indeed, we reached at least consensus on the fact that we have to go beyond it. We don't know how and towards with direction, with certainty, but we reached this result, this conclusion. Now, what do you think about this reading? Are Finzi's words, in a sense, useful to provide us lenses to read the history of the second half of the 20th century, basically, to understand what we did in black hole physics from the theoretical standpoint?
Mm. Well, let me see. I don't know if I fully capture everything that you
Yeah, sorry, I was
said,
lost.
but I mean, from my point of view, what I know, it is true that the boundary construction, so all these tips and peaks and all these things, this is something that is it is an extra construction. It's something that it doesn't come with theory, but it has a purpose. It's a purpose of trying to imagine or see whether it's a structure, and you can say things and about these parts where either there is incompleteness or you are at infinity, because these things works both for infinity and the singularities. And then this is when you can, in this sense, you can say things like the singularity is in the future or is in the past, or it is. I don't know, it is spherically symmetric, or I don't know. You can give properties to the incompleteness. So this was the purpose, but it is true that this is alien to the theory. I mean, this is a construction that you add to your theory with that purpose. Now, from my point of view, the important thing about the Penrose theorem is that you don't have to do anything alien. What you prove is that there is incompleteness. You follow this path with your light ray or with the time-like curve, and this finishes without any reason.
Yeah.
And you don't need to add the ideal point at the boundary. You don't need to add it. You are talking about just curves within your space-time. And therefore, I mean, to me, this is a very clever idea. You are saying, okay, there is a problem here. I don't know where it is. I don't know how it is. I cannot talk about it, but there is a problem. And I know this just from my theory without any addition. So this is what I can say. I don't know if this grasps what you were mentioning or not, but yeah, this is my
It's
opinion.
no, of course it fits well with this idea. Also because Finzi didn't in 1958 he couldn't know that there would have been, all the development of the boundary construction program and so on. But um, it is as if he was saying the only way we have in order to proceed in our research when we consider the singularity problem in GR is to build up research programs that I mean, there is even a sort of mathematical reason for that. So
Mm.
he gave a sort of mathematical explanation for that because he could master the mathematics of the theory. But of course, we are looking for a physical explanation for something that, of course, we express mathematically and so on, thanks to the theorems and so on. But of course, Penrose's theorem is not just mathematics, it's physics. It takes into account the gravitational collapse. And we know that the theory of star collapse is physically very cogent. So, of course, well, the different models that we have that talk about the gravitational collapse of stars are I mean, physically relevant, robust, however, of course, imply calculations. It's very hard then to solve these equations, but we do have models that enable us to do that. Anyway, no, thank you very much. I don't know whether there are other uh, questions. Otherwise, we can. Stefano said that he cannot talk. He is at the library or something. So, Alessio, do you have other questions?
Well, just a very quick one. You mentioned that a very important ingredient is global hyperbolicity. Is this correct?
Yes, but I mean, I want to.
But does it make sense to speak about this kind of things with in space-time that are not globally hyperbolic?
Yes, of course.
Okay. So
I mean,
that's the
the
question.
original Penrose theorem assumes a Cauchy hypersurface, and therefore it is globally
Yeah.
hyperbolic at the time. And but then the other theorems do not assume that. But in
Uh,
any case, I mean, if you look inside the theorems and the proofs and things, you are always doing calculations within a region,
Mm,
which is not the total space-time, but
okay.
smaller
So
region is globally hyperbolic.
at least locally.
But of course, the Hawking-Penrose theorem and many others do not assume global
Mhm.
hyperbolicity. Yeah, but I mean,
Okay.
not assuming global hyperbolicity is basically the same as saying that you are going to have Cauchy horizons and therefore extensions beyond
Mm.
things that you do not control and things like that. But still, there are theorems. Yes. Yeah.
Thank you.
Okay. Okay. So maybe.
Thank you very much. So we thank our speaker again. Thank you very much, Professor.
Yeah. Yeah.
It was a
My
pleasure
pleasure.
to
Yeah.
hear with us today.